Exponential Functions, Chapter 5, Section 3. The law of exponents. If m, n, a, and b are real numbers with a greater than 0 and b greater than 0, then a to the m times a to the n is equal to a to the m plus n, and a to the m divided by a to the n is equal to a to the m minus n. Now, these laws should not be new to you. You should have seen these before. So this is just more of a review of these laws. So I'm not going to go through numerous examples of them. Also, the power rule, a to the m to the n. So a power raised to a power is equal to a to the m times n. A times b to the n then can be distributed through, giving you a to the n times b to the n. Remember, that does not work with addition. You can't do a plus b to the n and have it be a to the n plus b to the n. Does not work. So it works for multiplication. Works for division. A over b to the n is equal to a to the n over b to the n. A to the negative n is equal to the reciprocal 1 over a to the n. So if you have a negative exponent, you can just change that from the numerator to the denominator and make it a positive exponent. Or if you have a negative exponent in the denominator, you can change it to the numerator and make it positive. And that's also equal to 1 over a to the n, because remember, 1 raised to any power is going to be 1. So you really have 1 to the n over a to the n, so that's 1 over a to the n. And then 1 to the n is equal to 1, just as I said. A to the 0 is equal to 1, where a is not equal to 0. 0 to the n is equal to 0, where n is not equal to 0. And of course, that leads to 0 to the 0, and I don't have that on this slide, but 0 to the 0 is undefined, because if you notice, if we follow that first rule, 0 to the 0 would be 1. The second rule, 0 to the 0 would be 0. So we have a discontinuity, a conflict. Therefore, 0 to the 0 is undefined. Now, exponential functions. Function of the form f of x is equal to c times a to the x. So now notice that the x is in the exponent. That's what makes it an exponential function. Where a is a positive real number, where a is greater than 0, right? A is not equal to 1, because if a is equal to 1, 1 to any value is just 1, so that would be a constant function, so it's not an exponential function. And c is not equal to 0, and is a real number, which obviously if c is equal to 0, then you just have the 0 function, f of x is equal to 0. So those should be obvious. The domain of f is the set of all real numbers. The base a is called the growth factor. And because f of 0 is equal to c times a to the 0, a to the 0, any number raised to the 0th power except for 0 is 1. So that gives you c, and so c is called the initial value. Many times in mathematics and science, we use a subscript of 0 to talk about the initial value. This is where it starts. So if you plug in 0 for x, that's going to give you the initial value, whatever c is. An exponential function, f of x is equal to c times a to the x, a greater than 0 and a not equal to 1, and c not equal to 0. If x is any real number, then f of x plus 1 over f of x is equal to a. Let's look at that again. So f of x plus 1 over f of x is equal to a. Well, what's happening here? We have c times a to some power. As that power increases by 1, what are we really doing? If we have a to the 4 and then we have a to the 5, aren't we just taking a to the 4th and multiplying it by a? So f of x plus 1 over f of x plus 1 is always going to be one multiple of a beyond f of x. So that's all you're doing. Every time you add 1 to it, you're actually multiplying by a, that base value. And if we solve that for f of x plus 1, then we have f of x plus 1 is equal to a times f of x. So you can take the result of the previous x value and now multiply that by a, and that gives you the next function output. So let's look at identifying linear or exponential functions. To identify whether you have a linear or an exponential function, compute the average rate of change of y with respect to x and the ratio of consecutive outputs. If the average rate of change is constant, then the function is linear. If the ratio of consecutive outputs is constant, then the function is exponential. So what it's saying is, if you move the input x by set intervals, and the output changes by set intervals, then the function is linear. So if you change the input by 1 and do that over and over again, and the output changes by 6 over and over and over again, then you have a linear function. If the ratio of consecutive outputs is constant, then the function is exponential. So if the ratio of consecutive outputs, so if you look at the output of the first input and compare it to the output of the second input, if that ratio, f of x over f of x plus 1, or you can do it the other way, f of x plus 1 over f of x, that's how I tend to like to think about it, then if that ratio is constant, then you have an exponential function. If it doesn't match either of those things, it's not linear or exponential. It's got to be something else. So let's look at identifying linear or exponential functions. So here I'm giving a table of x and y values. So when x is equal to 2, y is equal to 18. When x is equal to 3, y is equal to 54. When x is equal to 4, y is equal to 162. So I want to determine if this is a linear function or if it's an exponential function. I've got my inputs, I've got my outputs. So the first thing I'm going to do is I'm going to look for the change in y between these outputs. Notice my change in x is constant. That's 1, 1, 1. My change in y, well, if I subtract 18 from 54, I get 36. If I subtract 54 from 162, I get 108. If I subtract 162 from 486, I get 324, right? 970, 2916. So I do not have a constant rate of change. I don't have a constant for my delta y. So delta y is not a constant. It's not a linear function. So then let's take it a step further and look for the ratio, or I'd call it the multiplier. 18 times what gives me 54? 3. 18 times 3 gives me 54. 54 times what gives me 162? 3. Or you can look at it the other way and say 54 divided by 18 is 3. 162 divided by 54 is 3. 486 divided by 162 is 3. Right? So we have a constant multiplier. If the multiplier is constant, then we have an exponential function. In this case, it's with a base of 3 because that is the multiplier. The multiplier is the base. So what is this exponential function? Well, f of x is, remember, it's equal to c times x, a to the x. Well, in this case, the base is 3. So c times 3 to the x. So that gives us generic, but we need to find out what c is, what that constant is. So the way we do that is we can choose any of our ordered pairs. I chose to use x equal to 2, y equal to 18. So I just plug those in. So f of 2 is equal to c times 3 squared is equal to 18. So I just plug in the x and y. So now that I have that, well, 3 squared is 9. So I've got c times 9 is equal to 18. divide both sides by 9, and we get c is equal to 2. So now I have my constant term. So I can create my function, which is f of x is equal to 2 times 3x. And remember, order of operations says the exponent comes first, then you multiply. So this is not the same as 6 to the x. It's 2 times 3 to the x. The 3 is raised to the x, and then it's multiplied by 2. Well, let's look at another example of this. Starting with another table. Now, when x is 5, y is 13. When x is 6, y is 17, et cetera, et cetera. So our first thing is we're going to look for the change in y. We already see we have a constant change in x. It's incrementing by 1. So change in y, 13 plus 4 gives me 17. 17 plus 4 gives me 21. 21 plus 4 gives me 25. 25 plus 4 gives me 29. 29 plus 4 gives me 33. So I see that the change in y is constant. If the change in y is constant, then I've got a linear function, and the change is a constant 4. Your rate of change in a linear function is the slope. So let's see if I can come up with the actual function out of this. Well, I can. And what I'm going to do is I'm going to use the point slope form, because I have 6 different points on this linear function, and I know the slope, so I can choose any of those. So I know the slope is 4. So I plugged it in. So I have y minus y1 is equal to 4 times x minus x1. I'm just going to use the first ordered pair, 5, 13. So I've got y minus 13 is equal to 4 times x minus 5. Distribute through the 4, y minus 13 is equal to 4x minus 20. Now, to be perfectly honest, there is absolutely nothing wrong with leaving it in that original equation of y minus 13 is equal to 4 times x minus 5. That's in point slope form. That is a valid form. But in general, for linear equations, we like to either put them into standard form, ax plus by plus c is equal to 0, or we like to put them into slope-intercept form. So I'm taking it to slope-intercept form. So now that I've got this, now I like to keep the larger value on, where it is, so that I'm not ending up with negative signs. So I see y on the left-hand side. What am I saying? Let's try this again. I'm trying to get to the slope-intercept form. So I want y on the left-hand side. I want the other things on the right-hand side. Y minus 13. So I'm going to add 13 to both sides, giving me y equals 4 minus 7. 4x minus 7. Well, let's look at the properties of the exponential function. F of x is equal to a to x if a is greater than 1. The domain is the set of all real numbers, or negative infinity to positive infinity, using interval notation. The range is the set of positive real numbers from 0 to infinity, exclusive, using interval notation. There are no x-intercepts. The y-intercept is 1. The x-axis, y equal to 0, is a horizontal asymptote as x approaches negative infinity. Okay. F of x is equal to a to the x, a greater than 1, is an increasing function and 1 to 1. The graph of f contains the points -1, 1 over a, 0, 1, and 1a. Now you may look at that and go, well, how am I supposed to remember that? Well, remember, we're dealing with a to the x. So if you plug in -1, you have a to the -1. Anytime you have a negative exponent, you can take that into the denominator and make it a positive exponent. So a to the -1 becomes 1 over a to the 1, or 1 over a. So -1 gives you 1 over a. A to the 0, any number raised to the 0th power is 1, so that's 0, 1. And then a to the 1 is obviously just a, so 1a. So those 3 points should be intuitive at this point. The graph of f is smooth and continuous with no corners or gaps. Well, how does this change if a is between 0 and 1? Well, the domain is a set of all real numbers from negative infinity to positive infinity. The range is a set of positive real numbers from 0 to infinity. There are no x-intercepts. The y-intercept is 1. So far, this is seeming the same. So what's different here? The x-axis, y equals 0, is a horizontal asymptote as x approaches infinity. F of x equal to a to the x, where a is between 0 and 1, is a decreasing function, right? Because what's happening when we have a greater than 1, any number that's greater than 1, as you multiply it together, is going to get larger and larger. Any number between 0 and 1 is going to get smaller and smaller as you multiply it together. So it's a decreasing function as 1 to 1. It still contains the points -1, 1 over a, 0, 1, and 1a. So that doesn't change. We're just really changing whether it's increasing or decreasing. And the graph of f is smooth and continuous with no corners or gaps. So let's try this out. Let's have a look at the function f of x is equal to 5 to the x. Well, the first thing we should recognize right away is that a is equal to 5, and 5 is greater than 1, so it's going to be increasing. So we already have our base of 5, and we know it's increasing. So now I'm going to find those 3 points that we talked about. Well, if x is equal to -1, then we must have 1 over a as our output, so that would be 1 over 5. So we have the point -1, 1 over 5. If x is equal to 0, then the output's going to be 1. And if x is equal to 1, then the output's going to be a. So we have 1, 5. So those are our 3 points. And because it's an exponential function, the x-axis is an asymptote. So if we plot this, all we need to do is plot those 3 points, -1, 1/5, 0, 1, 1, 5, and realize the x is an asymptote. So what's going to happen is we're going to start close to the x-axis. We're going to curve up through those points and have a nice exponential growth there. Now, something that I do want to point out about this is the base function a to the x, where a happens to be equal to 5. All of the same graphing methods that we have used, the transforms that we've used, vertical stretch, vertical shift, horizontal shift, all of those things can still come into play. I could start with 5x as my base, 5 to the x as my base function, and I could make that 5 to the x minus 2. Well, since x is being affected by that -2, then that would be a shift to the right by 2. I could make it 5 to the x plus 3. So I'd have that 5 to the x function, it would be shifted up by 3. Realize that as it shifts up or down, that the asymptote is going to shift up or down by that same amount. So all of the things that we've used before for transforms work for the exponential function too. But I'm not going to go through and show that to you because it's the same thing that we've done over and over again. So let's talk about the Euler constant. Yes, that's Euler. It's not Euler. Euler constant. The number E is defined as the number that the expression 1 plus 1 over n to the n approaches as n approaches infinity. Now, if you look on your calculator, you have an e to the x button or an e to the, and it has a little square there button, or just a button that says e. Okay, so e is an irrational number like pi. It's approximately 2.718281828, and then it keeps going, but it does not repeat. It never ends. So it's Euler constant. And you can see that if you plug in 1 as the exponent for your e key, you're going to see that approximate number. Well, in calculus, this would be expressed using limit notation as E is equal to the limit of 1 plus 1 over n, all raised to the n, as n approaches infinity. That's what all that says. So this is breaking into some of the things that you'd be dealing with in calculus. Imagine that in a pre-calc course, we're preparing for things that you'll see in calculus. Okay, so let's look at the law of exponents. If a to the u is equal to a to the v, then u is equal to v. That should make sense, right? Obviously, if you have a to the 3 is equal to a to the x, then obviously x has got to be 3, right? If you have the same base with different exponents or different variables for those exponents set equal to each other, then the exponents have to be the same. Therefore, if 7 to the x minus 6 is equal to 7 to the 4x plus 2, since the base is the same, then x minus 6 must be equal to 4x plus 2. So we have a way to get into the exponent if the variables are there and solve. So yeah, x minus 6 is equal to 4x plus 2. So if we put the x's on the same side and the constants on the same side, we have 3x is equal to negative 8. Divide both sides by 3, we have x is equal to negative 8/3. So that's the law of exponents. One side note that I'll mention, and you may run into this, you should have seen it before, but you may run into this here, is that you won't always be given the same base. But if you can create the same base, then you can do this. So if you had 3 to the 5th, well, actually, let's make it 3 to the 6th is equal to 9 to the x, you could still work that. 3 to the 6th, you could make 3 squared to the third power, right? Power rule says the exponents multiply. So you could have 3 squared to the third is equal to 9 to the x. 3 squared is 9, so that's 9 to the third is equal to 9 to the x. X must be equal to 3. So look at that and think about it. If you have bases that don't match, that aren't the same, look and see if you can break up that exponent to turn one of the one that's smaller into that other base so that then you can use this rule.